Today's lesson is titled Operations of Functions. We'll be finding domains from an equation. We will also be combining functions. And lastly, we'll be taking the composition of two functions. First, in finding the domain of an equation, I'd like to remind you about what a domain is. Often we say that the domain of a function is the set of all x values. When finding the domain of a function, we're going to begin by assuming that the domain is all real numbers, or written in interval notation, negative infinity, comma, positive infinity. Then we're going to determine if there's any place where the function is not defined. And then we're going to exclude those values from the domain. The two types of functions who have excluded value are rational functions and even root functions. Rational functions have excluded values because you cannot divide by a zero. You're never allowed to have the denominator being equal to 0. So let me give you an example of what I'm talking about here. If I give you an example, f of x equals x minus 4 over x plus 3, this is a rational function because we have an x and a fraction. We have x's in the denominator, we have a rational function. Whenever you have an x in the denominator, and because x is a variable and it can change, we have the possibility that when you plug in a value for x, we might get a 0 in the entire denominator, and that's not okay. So to identify these bad values that do not belong in our domain, we're going to set the denominator not equal to 0 and solve. Don't forget to write your domain in interval notation without these excluded values. So for the example that I gave you, f of x equals x minus 4 over x plus 3, because we have an x in the denominator, this is a rational function. And because we have a rational function, we have to exclude values of the domain. And the value we're going to have to exclude is where the denominator is equal to 0. So I'm going to set this denominator not equal to 0 and include all the values that are not equal to 0. So x is not equal to negative 3. And my domain would be all the values that are not equal to 3. That would be negative infinity till negative 3, union negative 3 to positive infinity. In this section, when we're trying to find domains from equations, sometimes I like to think of f of x as like a party planner, or you're setting up a party here, and the domain is like your invitation list. Who are we going to invite to the party? Well, we always assume we're going to invite everybody to the party, and we're just going to take out the one invitation that we don't really want to include. In this case, because I have a denominator, I really don't want that denominator to be equal to 0. So I'm going to include everybody. Everybody gets to come to my domain party except that negative 3. So I send out all my mass invitation, and then I just make sure that negative 3 doesn't get the invitation. He's not included in my domain. And we're going to use this a little bit later as well. For my even root function, I have excluded values because I cannot take the square root of a negative. Or I should say, I cannot take the even root of a negative. To identify the qualifying values that do belong to the domain, notice that I'm talking about the ones that do belong, I'm going to set the expression under the radical, called the radicand, greater than or equal to 0. Let me give you an example. F of x is equal to the square root, which is an even root, of x minus 4. I'm allowed to invite everybody to my domain party here. Everybody except, well, because I'm an even root, I can't take this even root of a negative. So everybody except where my radicand is negative. So what values am I allowed to use? Well, I'm allowed to use all the values where x minus 4 turns out to be greater than or equal to 0. Those are all the people that I'm going to invite to my party. All the values that make the radicand greater than or equal to 0. After solving this inequality, I'm getting x is greater than or equal to 4. So that's my invitation list. I'm going to include everybody that's greater than or equal to 4. So 4 to infinity. And that is my domain. So in summary, invite everybody to your domain. That's all real numbers that get to be invited to your domain. But if you have a rational function, make sure you take out the invitations for those that have a denominator being 0. For the even root functions, well, they don't really like negatives underneath their radical, so we're going to take those out of your domain. Looking at the first example, f of x equals x squared minus 7x. Again, if I'm considering this kind of like a party, I'm going to invite everyone to my party to begin with. Then I'm going to take out the invitations to those that make problems, okay? We don't want to invite those bad problems to our domain party here. So I want to think about, does this have a rational function? Do I have an x on the denominator? Well, no, I don't. So there's no problems there. I'm never going to be a denominator of 0 because there's no x's on the denominator. Do I have an even root here? Well, no, I don't. So my domain is going to include all real numbers, negative infinity to positive infinity. There's no bad values or needed to exclude any values, so I use all real numbers. Whereas the next problem, g of x equals 3x plus 2 over x squared minus 2x minus 3, has a denominator. There's no even roots here, but there is a denominator. So I am concerned about where the denominator is equal to 0. So in order to find out where my domain is, I'm going to take all the numbers that are on the number line, except that place where the denominator is going to be equal to 0. So to find that one place that the denominator equals 0, I set the denominator not equal to 0. I'm including all the values as long as they're not equal to 0. I can solve x minus 3 can't be 0, x plus 1 can't be 0, so x is not allowed to be positive 3 or negative 1. What can x be? Well, everything else, everything on my number line except negative 1 and positive 3. So I'm going to punch out little holes there using my open circles, and I'm allowed to use all the values on the number line as long as they don't include negative 1 or positive 3. To finish writing my domain in interval notation, I have 1, 2, 3 intervals, so I'll have 3 interval notations. Negative infinity to negative 1, union negative 1 to 3, union 3 to infinity. I get to include everybody into my party except negative 1 and 3, and so that's my domain. Similarly, on the next problem, h of x equals x minus 4 over x cubed plus 9x squared plus 8x. I don't have an even root, but I do have a fraction, and on my fraction I have x's in the denominator, which could give me the possibility where my denominator might be equal to 0. So in this problem I need to exclude all values where the denominator is equal to 0. So I'm going to set my denominator not equal to 0 and solve. This looks like I have a GCF of x. I get a factor. So x is not allowed to be 0 from the first factor. X is not allowed to be negative 8 from the second factor. And x is not allowed to be negative 1 from the third factor. Who is allowed in my domain party? Well, everybody else. I'm just not allowed to be 0. I'm not allowed to be negative 1. And I'm not allowed to be negative 8. So I'm going to take those invitations out of my party list and include everybody else in my domain. I have 1, 2, 3, 4 intervals. So my domain written in interval notation is negative infinity to negative 8, union negative 8 to negative 1, union negative 1 to 0, union 0 to infinity. Notice because I have 1, 2, 3, 4 intervals, I should have 1, 2, 3, 4 interval notations. Our next problem includes an even root. H of x is equal to the square root of 3x plus 2. Notice a square root is an even root, and I need to exclude the values where I'm taking square roots of negatives. I'm going to include all values on my number line except where my radicand is negative. So to find the values that I can include, that do belong into the domain, I'm going to set the radicand greater than or equal to 0. My radicand, again, is the expression underneath the radical, or 3x plus 2, has to be greater than or equal to 0. And as long as this restriction is satisfied, I'm allowed to include all those values. To solve the inequality, I subtract 2 and divide by 3. Notice I'm dividing by a positive 3. I do not need to switch my inequality because I'm not dividing by a negative. I understand that there is a negative in the right-hand side of the inequality, but I'm not dividing by the negative. I'm only dividing by a positive 3. Do not switch your signs. So I'm allowed to be negative 2/3, so that's a closed circle, and anybody greater than it. I'm not allowed to include anybody below this because if any value to the left of negative 2/3 would give me a negative under the radical, and I've already excluded those from my domain. These even root functions don't like having negatives under the radical, and so they're not going to include them in their domain party. They're going to kick them out. Nope, no thank you, don't come to my party. I only want things that are going to make it positive under the radical. Similarly, our next problem, p of x is equal to the square root of x plus 3 plus the square root of x minus 5. We have two even roots. And because we have two even roots, I need to set both of those even roots greater than or equal to 0. And then we'll discuss how to choose the domain from there. So I have x plus 3, the radicand for the first radical, has to be greater than or equal to 0. We also have x minus 5 has to be greater than or equal to 0. I can solve each of these inequalities. X is greater than or equal to negative 3. And we also have x is greater than or equal to 5. Well, if I graph both of these, I have some overlapping parts and some parts that are not overlapping. To graph the blue, x is greater than or equal to negative 3. I have a closed circle at negative 3 on all the values to the right. To graph the red, x is greater than or equal to 5. I have a closed circle at 5 and all the values to the right as well. So the question is, well, what's the domain of the real function p of x? P of x has both the blue radical plus the red radical, and we want to be defined for both. So let's think of this blue one as a domain party. In the blue part of the function, we're including all values greater than or equal to negative 3. He's going to let everybody that's negative 3 or greater into his party. Well, the red guy, he's a little bit more strict. He's like, well, no, I'm going to include everybody that's 5 and greater into my party. Well, if they're, well, I don't know, so let's say co-hosting this party, who are they going to allow into their party? If the red function says, no, I'm only allowing values that are greater than or equal to 5, then the blue function can't invite any of these values to their joint party. The only values that we're allowed to use are the values that are both in the red part of the function and the blue part of the function. We need the values underneath the radical to be defined to be positive so that the function can be defined for both the blue part and the red part at the same time. So even though the blue part of the function is defined between negative 3 and 5, it's not defined for the other part of the function, which makes the whole p of x undefined from negative 3 to 5. So the only values I'm allowed to include are the places where they overlap. My domain for this function is going to be 5 till infinity, because both the red and the blue restriction are satisfied at the same time. And that's why my domain is only from 5 to infinity. On my last problem, q of x is equal to the square root of x plus 8 divided by x minus 3, I've got two problematic functions. I've got an even function on the top, meaning that the radicand has to be greater than or equal to 0, but also I've got a denominator here with an x in it. Whenever I have a denominator with an x in it, I've got to exclude the value where my denominator is going to be equal to 0. You can think of this as two parts of your function. The even root function has his own invitation list. X plus 8 has to be greater than or equal to 0. That's what's going to satisfy him for his domain. Similarly, on the denominator, x minus 3 cannot be equal to 0. So the denominator will include anybody except where that one place is equal to 0. Whereas the numerator is including everybody as long as my radicand is positive, or 0. When I solve these, I'm getting x is greater than or equal to negative 8 for my blue part of the function, and x is not equal to 3 for the red part of the function. Graphing these, I'll start with the blue. The blue value says, okay, I'm allowing all x's that are greater than or equal to negative 8. So I make a mark at negative 8, and I'm going to include all values from negative 8 to the right. Well, the red part of the function, he's going to include anybody he wants except for 3. So if you want to think about this, we could start with the blue function, the blue graph, and the red part of the function, he's like, yeah, okay, that's a fine invitation list, except we're not allowed to invite 3. It would just not be very fun if we included 3. So we're going to put an open circle at 3. So I'm just going to come in and erase the blue line, make it a little bit neater here. I'm allowed to have all values up until 3, but not equal to 3. So the red value would come in and put like an open circle right there. My domain for the whole function q of x includes negative 8 until 3, union 3 till infinity. Notice I'm not allowed to include the 3, so I use parentheses on the 3. And that's my domain, having both types of excluded values in the same function. That concludes our discussion on finding domain from an equation. In the next video, we'll be talking about combinations of functions.